So what I do is light matter interactions and quantum computing. This is part of the research that I did with um, a group at UConn and the University of Colorado at Boulder and Harvard. So basically, quantum computing, well, uses quantum mechanical phenomena. And so in my situation, you represent your data by the properties of some kind of atoms or molecules because you're trying to make your system run in a solid state device. Quantum computers possess the abilities that classical computers don't have. And you can, some of the things is that it can factor large numbers really fast or can implement very efficient database searches. So basically, they're really fast. And that's, one thing that they're very useful for. And so let's talk about what a qubit is, which is basically it's a basic unit of quantum information. And so, your bit is either a 0 or a 1, which everybody knows about. And a qubit is basically, can be a 0 or a 1 or a superposition of both, which is, part like half dead cat, half alive cat. And so you can write out your state like this. And so a few rules is that your alpha squared and your beta squared here have to equal 1. And I'm not going to go into huge amounts of detail, but you can represent it this way with your, 1 bit like this, your 1 state like this, and your 0 state like this. So your, 5 state is somewhere in the middle. So what does that have to do with anything we're doing? Well, let's talk about a few things, physical implementations. And there are a couple of gates that we use. One's called a Hadamard gate, which is a way of basically changing your state into other states or combining your the state of your qubit and combining the state of 2 qubits or turning your qubits into some other form. So basically, if you use a Hadamard gate on a 0 qubit, it turns it into a combination of these. And if it's a 1 qubit, then it goes, it looks like this. But what we're interested in is something called a phase gate. And that basically is represented by something like this. And you have 1, and here it's not, any of these, it's an e to the I phi. And this is basically a phase. And when you apply this phase gate, under some circumstances, you can change your 0 state into a 0 state, but your 1 state, you can engineer, you can turn it into either another 1 state or a negative 1 state or something else. So why is a phase gate important? Again, it's because you can change your states into other states while leaving some states the same. So again, a phase gate itself is part of what's known as a C0 universal gate, which is a gate that's used in quantum computers. And so what we're doing is basically trying to figure out how you can actually make a phase gate. And so when you want to make a phase gate, what you want to do is you want to find out how you can actually engineer this thing here, which is a phase. And how you would do that is basically create what's called a nonlinearity. So this is where it actually goes. This is where basically the quantum information theory itself goes into like an application. How do you actually do this? So these are basically states in an atom. So, you can have, you can expose your atoms to electric fields or magnetic fields, and you can have, different energy states. So this would be a ground state. This would be like a first excited state. This would be a second excited state. So normally what you would think of in real life is that, well, you use a certain amount of energy hopping up here, you use another amount of energy hopping up here. And then if you go from here to down here, it would be the same amount of energy. However, for various reasons, this is not exactly true. This depends on the structure of the atom and other energy losses and stuff. So, and how your entire system is constructed. So basically this 2 minus 0 is not exactly twice one of these. It should be, if these are evenly separated, it should be. And technically this should be 0, but it is not. So basically you try to figure out what this is and how you can actually achieve the system. So you have different ways of doing it. You put in defects in atomic lattices, and that would actually create this sort of splitting. Or you can use dipole-dipole interactions. And so, one of the biggest study is like, how can you actually do this, and how can you actually create a system where you do get this type of nonlinearity? So the projects that I've done and are working on currently, that some solid state systems that achieve a phase gate. So basically, how do you end up doing this? What types of material can you use? So the possibilities are endless. You can take different types of material. You can see what happens when you dope them with something. You can see what happens when you take, various types of dipoles and how they interact with each other. We work in 2D and in 3D. I also do general light matter interaction. And also, of those of you who have done math methods too with me, you know that I like group theory. So basically, I do a lot of group theory analysis of atomic energy levels, and how do you actually find out what energy levels are in each atom, because when you do like a spectroscopic study, it's really hard to figure out which energy level is located and what it actually corresponds to, whether it's like a 1 or a 2 or S or P, and so on. So you use group theory to find out which energy levels are exactly what in a solid state system. And I also do quantum information and quantum machine learning. I work in collaboration with a group at Harvard University. We have a group meeting every week, and everybody does presentations, and we discuss what we are working on. And it's basically very fast evolving and very current. Anybody who wants to join, please let me know. So thank you, and thanks for asking me to participate.